Alright, hi everyone. Here is a recording of the second lecture for continuous optimization. If you're trying to follow through on the slides, I'm going to jump forward a little bit and then kind of come back to the beginning of the slides. So I'm jumping forward to slide 11. Just going to go through some definitions of continuous convex optimization, and then we'll go back towards optimization with constraints, which is actually the start of the slide deck. So convex optimization is likely one of the best understood areas of optimization. It does require quite a few assumptions and meaningful assumptions. In other words, it does kind of limit the space of problems we can work with. But the good news is that when we do find a problem we can represent in a way that fits convex optimization, then we have kind of global optimality properties and efficient methods for working with these problems. And so, these assumptions on both the objective function as well as the constraints do end up having kind of tangible benefit downstream for us. Again, when we can, represent a problem in a form that fits a particular kind of convex optimization problem. And we'll look at two at the end, namely linear programming and quadratic programming problems. But as I said, let's start with some definitions. So we're going to look at a convex set to begin with. So let there be a set C, and the set C is a convex set if for any x and y in that set and some scalar theta in the range of 0, 1, we have that the linear interpolation shown in equation 24 here is also within the set. Okay, so this is a linear interpolation, and you can see the degree to which we are favoring x or y in this case is defined by theta. So in the extremes, when obviously theta is 0, this falls away and we're just left with y. And then in the case when theta is equal to 1, this falls away and we're just left with x. And then anything in between is represented by kind of how far between x and y we move. So let's take an example here in these two regions below. So the green shape on the left is a convex set. I can take any 2 points in the set, and if I draw a line between it, then all points between those two endpoints, those two extremities, lie within the set. Okay, so it's not just about being able to find a theta in the range. In this case, we need all thetas in the range of 0 to 1 to still satisfy this property of lying in between our two endpoints. All right, the shape on the right-hand side does not satisfy this property. We can look at the top here. So I have 2 points. Let's call it A and B. They both lie within the red shaded region. But if I draw a line connecting points A to B here, we now have this region over there, which is lying outside of the shape, right? You can see the blue line has now left the red shaded region. And so there is some value for theta such that the line connecting A and B goes outside of the shape. And so that there is a linear, in the linear interpolation, it doesn't stay completely within the shaded region. All right, so that's the notion of a convex set, and that's going to help us define what we really care about, which is a convex function. All right, so let f be a function. It's mapping d variables to a single scalar in our case. We're going to say, so let it be a function whose domain is a convex set. Okay, so this definition we just had now, we're going to say for all the values of x in the domain, those values of x need to form a convex set, and you'll see now why in a second, why we need this to be true. The function f is a convex function if for all x and y in the domain of f and for any scalar theta you have the following property. Okay, so in this property says that if I take a linear interpolation between 2 points in this domain, okay, so they are points that I could possibly put into f, any linear interpolation between these two endpoints is going to then be fed into the function. And again, this is why you need a convex set, so that any kind of choice of theta here will still give me a valid value that I can pass into f. So regardless of how I pick theta, if I have x and y, any point in their linear interpolation will still be a valid value within the domain of f, and it's still a valid value I can pass into f. So if the domain wasn't a convex set, then it's not guaranteed that this value I'm going to pass into f here would be a valid value. All right, it might be outside the domain, and so then we have a problem. So to begin with, this is where that assumption of the convex set in the domain is necessary. Anyway, I'm going to pick two endpoints in the domain, okay, and I'm going to take some linear interpolant between them, pass that into the function. That value that is produced by the function must be less than if I instead evaluate the function at the two endpoints and linearly interpolate with the same theta between the two endpoints. You can see this as an example here. So let's say that, minus 2 and 3 are my x and y values here, my bold x and bold y, so my two endpoints. Then this property on the left here says that I'm going to find some point that lies between them in the domain. So let's say, this point here for whatever theta that is. It's 1, 2, 3, 4, 5. So let's actually just go, 0.4. Theta is 0.4, in which case I'm going to actually lie at 0, right? So now I have found along this kind of line interpolating the domain, I found my kind of point in that interpolation, and I'm now going to evaluate the function at that point of 0, and so my function is over there. Okay, so that's what I've done here. But now let's look at green instead. I'm going to instead evaluate the function at the two endpoints and do a linear interpolation of those endpoints, those two values at the endpoint, and evaluate the function there. And so you can see now that the red line is always, any point in this red line is always lying below the green, right? And I can draw it in blue just to make it a little bit clearer to our example. So any point here in this linear interpolation between -2 and 3, if I first interpolate, then pass it into the function, it's going to lie below it's going to lie below the green line, which is where I first evaluate the function and then linearly interpolate that. Okay? If this property holds, if it is true that that blue line is always below green, then we have a convex function. Okay? And so that was kind of a visual proof, but you can just think of it as interpolating the domain and then evaluating the function will always be less than if I first evaluate the functions and then interpolate the output. There are other conditions, and they are somewhat equivalent. Depending on the property of the problem that you're looking at is which one is easiest. They will all kind of come to consistent answers. So if a function f, again, mapping from n dimensions to a scalar output is differentiable, we can specify convexity in terms of its gradient. So this is known as a first order criterion. So for a differentiable function, a function f of x is convex if and only if, for any 2 points x and y, the following holds. If I take a point x in the domain and then evaluate its gradient and then approximate how much should change when I move to y using that gradient, it's going to lie below actually evaluating the function at that point. Okay, so again, let's say I'm looking here at x. I'm going to now get the gradient at this point here. Okay, that defines a line. And so now, if I want to move to some point y over there, let's say y is this point here. Now, f of y, which is the green point, is lying above this kind of blue line that's defined by the linear approximation of the function using just the gradient. Okay, and so that's exactly what this says. On the left-hand side here is the green point, so it's just what happens when I evaluate the function at a particular point. And then on the right-hand side, it says I'm going to start off at some blue point over here. So this is my f of x there. I'm going to get the gradient, and I'm going to use that to define a line approximating this function f at a point. And so it is the closest linear approximation at this point f of x. And so every point in the blue line is now going to lie below the function itself, the red line. And so that now means that is, in terms of the first order criterion, that means that this function is also convex. Okay, You can see how if this wasn't true and we had a function, let's say there was this bit here where it started, sorry, wrong color. Let's extend the function. I've now made it non-convex, but if it goes far enough, and let's say we're, approximating at x over there, we have a line passing through it, and there's now this point where actually the blue line is sitting above the red line over here, okay? And that's because this region that I've just drawn over there stops being convex and it becomes concave in that area. Same story just for the, let's say we're looking at this criterion over here, from equation 25. Let's finish drawing this line again. Same story, now I can contradict this criteria. So let's say I'm going to interpolate from, what's a good version of this? Maybe over here to over there. If I am interpolating, I'm doing this on the fly now. This should be lying above. Oh yeah, okay. So if I'm going to interpolate my x and y points, I'm going to end up over here. And on the other case, I'm going to actually evaluate my function, and I'm going to be in those two endpoints. And so now what is green, this bit here, should be lying above the function. It's actually lying below it, because I've just drawn this on the region that is now concave and not convex. Okay? Whereas on this side here, if I drew two endpoints there, it's on the region of the function where it is convex. And so now green is lying above the red point between those two boundaries there. Okay, so I hope that also kind of just showing the point where it's also contradicted maybe helps with the understanding. The last criterion that we can look at is the twice differentiable version, so it's the second order criterion. And that's just so that if we have a function, f of x is convex, if and only if its second derivative is positive semi-definite. Positive semi-definite means that it might be 0, but it can never be negative. And so we know that the second order criterion, or the second derivative, if it's negative, it means the function, its gradient, is starting to decrease when I evaluate the function at different points. So the gradient at different points on the function. So in this case, this gradient over there is sharper or larger than that gradient there, which is larger than that gradient over there. So as I move to the right-hand side of the function, my gradient is getting smaller and smaller until it actually eventually just becomes negative. Okay, and so in that case, the second derivative, which tells me how my gradient is changing, will be negative, which says that it's getting smaller and eventually becoming negative. All right, that is a concave function, and so for this to be convex, we know it needs to be positive. The gradient always needs to be getting larger and larger. So if I evaluate the gradient there, that's negative, then over here it's around about 0, over there it's positive. So my gradient is starting with negative, becoming 0, and then getting positive and more positive, so it is convex. Okay, so those are the three criteria of convexity, and you can see an example here. So in the textbook, you can see a more kind of full exposition of this example. We're just going to look at one criteria, but you can prove that this function is convex for all x greater than 0, and the reason it has to be x greater than 0 is because of the log. X negative doesn't exist for the log. So if you want to see more of this, you can see example 7.3 for an intuitive sense of why this function is convex, using the two possible tests, but example 7.3 is not a proof, as it's kind of just a statement. But we'll just show that this function is convex using the Hessian, the second order method. Okay, so let's differentiate this function. You can actually see that this is a product rule, so we're going to differentiate this first term, leave the log 2x the same, and that's exactly what's happened here. We differentiated x, we got 1, and then the log 2x stays the same over there. And then we're going to then add that to the term we get when we then differentiate the second term, leaving the first one constant. And so the derivative of log 2x is just 1 over x ln, the natural log now, of 2. Okay? And you can see the x out front over there is just this x over here out front there. Okay? So that's just the product rule. We've differentiated the two separate terms and then added them together. Okay, ultimately then this x cancels with that, and we're just left with this term on the right-hand side. This is our first derivative. We're then going to differentiate it a second time, and so this term here has no variable of x, so it becomes 0. And so what we're left with is just the derivative of log 2x, which we just saw is once again x ln 2. Okay? And so now in this case we evaluate whether or not this is positive semi-definite. And as we're considering only x greater than 0, again, because that was only the part of the domain that our function was defined on. All right, so we've only defined this function for x greater than 0. Every value of x in this case is a convex set. All right, because any value of x greater than 0, when I add them together, some linear interpolation between those two values is still going to be a value greater than 0. And so we have this convex set, x greater than 0. So that is fine. We can then say, well, if x is greater than 0, then we know that x ln 2 is going to be greater than 0, right? Because ln 2 is also positive, which means that 1 over x ln 2 will be greater than 0. Okay, and ultimately that means that the second derivative is greater than 0, and so f is convex by our second test. All right, and so that's kind of the one way to prove convexity. Well, we can use any of the three stated tests. There are other equivalent ones. It can be sometimes rather tricky in practice. Luckily, convex functions are closed under certain operations, which we can use to then simplify proofs. And if you go deeper into this topic, you'll kind of start to care a lot more about these different techniques. Specifically, for example, if f1 and f2 are convex on A, some domain A, then so is a conic combination of those two functions. And a conic combination is essentially a more general version of this linear interpolation we've been looking at, where we just have alpha and beta being any two values greater than or equal to 0. Okay, so it's a slightly more general version of what we've been talking about. Turns out these functions are also a conic combination of two convex functions, is itself convex. Similarly, the application of an affine map preserves convexity, so you can map these kind of output of these functions around. And then lastly, the one kind of that I think is a little bit more intuitive is that pointwise supremum preserves convexity. So for example, if you're taking the supremum over a set of convex functions, you will get out a convex function. And I've drawn an example here where we're going to say this red and the the red and the green functions are two convex functions. You can see that they're both kind of curling upwards. And I'm going to take the supremum of the red and the green functions at all points. So for every point, let's not use blue, let's use a completely different color. So I'm going to now say at every point on this function, I'm going to look and I'm going to see, or in this domain, I'm going to look and see which one's larger, red or green, and then I'm going to trace that outline and call that my new function, f of x. And I'm drawing that f of x with blue. So for example, over here, red is greater than green, and so that's my points in the supremum. Same for here, red is greater than green, so I start to outline it. And then I get down to this point here where they're equal, all right? And then that doesn't matter, I just pick one. And then anything to the right of this, I see that now green is greater than red, so I start tracing out the green. And we keep tracing out the green until once again we get to a point where they intersect. And now I start tracing out the red, because that's the supremum. And you can see that this purple line I've now drawn, or it was blue earlier, traces out a new function, f of x, which is itself convex. It's itself curling upwards. And so this is just kind of largely dealing with the fact that by taking the supremum, I know I'm always going to be sitting at the largest value possible. And so since all of them were curling upwards, it's impossible for me to kind of have a gradient that starts curling down when I'm always just looking at the largest point of all of them. Okay? And you can kind of prove these a lot more generally. All of these are kind of relatively deep. I just think this slide is here to give a little bit of intuition of how you can manipulate these objects and treat them as structures in their own right. Okay, this is now the point where I'm going to jump back to slide 1 because it's talking about convex optimization. So we're now back at slide 1. And I'm now going to talk a little bit about constrained optimization. And again, constrained optimization uses these properties of convex sets, which is why I wanted to talk about that to begin with. So we can extend our previous optimization discussion from continuous optimization lecture 1 to one in which we now have constraints. Specifically, we're going to try and minimize some function that's f of x. But now, this is kind of what we initially started with when we were talking about gradient descent and Nesterov momentum and all of those sorts of things. But now, we are subject to a set of functions, these gi's, and there's going to be m of these functions. And we're going to say that for all of these, they're a function of x, and they must be less than or equal to 0. This less than or equal to 0 may seem restrictive, but in general, it's just the same as then saying, like negative gi of x is greater than or equal to 0. Or for equality, you'll then just have both, and the slides do touch on that in a second, or in a couple of slides. So in general, you can try and make any function fit this less than or equal to 0 constraint. And so in this case, where the gi's are also a function of rd dimensions, so the same input as our normal function f, mapping onto an output scalar, and those are the constraints. These are the functions that we don't want to violate. We don't ever want to be in a position where a function gi outputs a value greater than 0. And so the question is, how do we solve this type of problem? And there are actually a number of ways to tackle this in optimization as a whole. We are, however, going to look at a specific classical approach often referred to as the penalty method. Okay, and so somewhat intuitively, if I wanted to solve this problem, I can represent it as follows. I can just give it the most harsh penalty possible, and so you would say, well, I want to define this function j of x. J of x is the same as f of x, which is just my original function that I want to minimize, plus the sum of an indicator function on all of my constraints. And this indicator function is also called the infinite step function. And this says that whenever the input to this function is 0, whenever this input to the function is less than or equal to 0, I output 0. And whenever it's greater than 0, I output infinity. In other words, whenever I violate my constraint, you can see g of x is less than 0 there is what I'm constraining to. If I ever violate that, I'm just going to have an infinitely large value. And if I don't violate that, if the input to this one function, this infinite step function, is less than or equal to 0, which is again what I want from my gi, then I just output 0, and it's the same as just saying, well, I want to now minimize f of x. If none of these constraints are violated, this sum evaluates to 0. Okay? And in that case, now my j of x is free to just be f of x, and I can minimize as you kind of usually would. The problem, though, with this is now that if I violate any one constraint, I now output an infinite value. You can see as it says, so basically j of x is pushing infinitely high if we violate a constraint. It says, why would j be hard to optimize? Well, because it's a step function. It's flat everywhere with this discontinuity at 0 where the step actually happens. So the function looks, I obviously can't draw it because of the infinity, but a step function looks something like that. Okay, so to this side the gradient is 0, to that side the gradient is 0, and then over here the gradient is infinite. And so we can't really use any sort of gradient optimization technique on this. It's very hard to evaluate, and it's very hard to kind of have any sort of gradual or algorithmic way of solving this problem. Okay, and so what we can do is try and maybe slightly weaken our approach and have a bit more of a subtle, nuanced approach to this problem. So just to note, keep track of that j is equal to this kind of infinite constraint version of this problem. So j is equal to my original problem I want to minimize. And again, that's in the definition that I have of the problem of constraint optimization. So f of x is what I want to minimize, plus the infinite stepwise functions that defines j. I'm instead going to define L here by adding a variable lambda. The lambdas are called my Lagrangian multipliers. Okay, and this function in general is called the Lagrangian function. Okay, and so it's a slightly more nuanced approach. You can see that I'm defining my Lagrangian the same way I defined j. I'm going to start off by saying, well, it's the same as my original function I want to minimize, but now I'm going to have the sum of a function of my constraints, but instead of it being the infinite sum, I'm just going to have a multiplier by lambda I. All right? And so we have concatenated all our constraints into a vector and all the Lagrangian multipliers into a vector. Then this just becomes a dot product. Okay, you guys should be able to see by now that when I have a sum over I and the two shared indices I over there, that is just the same as doing a dot product. Okay, and so this is the form of the problem that we kind of care about right now. We have the function we want to minimize plus the dot product of all our Lagrangian multipliers with all of our constrained functions. Okay, so this is a little bit more nuanced. At least it's not going to output infinite values necessarily. And so for kind of values of g that go beyond 0, that kind of increase, we now have the fact that this is going to be pushed up. So if I wanted to try and minimize L, I still want to keep g low so that I don't push the second term up. But at least now this is a function that I can just, actually work with. Those are not infinite values. Similarly, I'm always going to want to be minimizing f of x to minimize L, so we haven't really violated that constraint yet either. Okay, we haven't kind of made our problem worse by doing this either. Okay, so this is a weaker condition, but obviously there are somewhat trivial solutions, such as setting lambda is equal to 0 or something, then this just all falls away. So we're going to have to do a little bit of manipulation, a little bit of thinking now around how we set our Lagrangian multipliers so that this still makes our problem useful and we can still actually avoid violating any of our constraints on G. Okay, you can see that that's the last point it says there. The challenge is now that we need to find both x and lambda. All right, so we've introduced a new variable, which makes this optimization slightly harder. Luckily, for a class of objective functions or constraints, we can convert this problem and solve the converted problem. And this is known as either being the primal is the original version of the problem, or the dual is this converted problem. Okay, and so we have this definition as follows. We're going to start off by just defining the original problem we care about, which is the primal problem. So we want to minimize some function f subject to our set of constraints, where we've written the constraints as the form of each function must output less than 0 or equal to 0. This is the primal problem, and it corresponds to the primal variables, which is the x's, which is the variables we actually care about optimizing. All right, we can then convert this and set into the associated Lagrangian dual problem. So the whole, the main term here is the dual problem. And this is given by the following. We're going to actually write this as a function of lambda instead of x. So the original primal problem is a function of x. The dual problem is a function of lambda. And instead of minimizing x, we're now going to try and maximize lambda. This lambda vector now in this case. And subject to the fact that our lambdas must be greater than or equal to 0. Okay? Again, the equality to 0 makes this somewhat trivial. Okay? But we are trying to maximize it. All right? So in most cases, because we're trying to maximize lambda, you don't want to go with 0. You want to try and go with something a little bit higher than that. So when your lambdas are 0, that's essentially like saying this is the worst case scenario for us. And so we're going to just land on the trivial solution and say that, well, actually, there's no way of optimizing this while considering your constraints. But for any value of lambda greater than 0, not equal to 0, we can say, well, we can actually optimize f of x while considering the constraints to some degree. But the whole point here is that because we're maximizing the lambdas, we are trying to be as strict on our constraints as possible. That's the whole idea, is that I'm not going to necessarily be so dogmatic about my constraints to use a infinite step function. I want to be a little bit more lenient, but not any more lenient than I necessarily have to be. And that's the kind of whole, quote, maybe philosophical approach to this. Okay, and so here the lambdas are the dual variables, and importantly, the definition of this dual equation, this d function of lambda, is that it is our Lagrangian where we've already minimized over x. Okay, so I'm going to take my original Lagrangian, and I'm now going to minimize with respect to x first. That then, because I've now minimized my x's, those are fixed. We've gotten rid of one of the variables. And so we're left with just lambda being the only thing left to deal with. Okay? And that's essentially the whole problem here, is that we want to try and first see, what is the set of solutions that satisfies x, that kind of optimizes x, and then we're going to try and then maximize our constraints after that. Okay, and we're now going to discuss this idea of that ordering of minimization, maximization now. Okay, so in order to understand why it is worth trying to solve the dual problem, we need to make a couple of observations. The first is called this min-max inequality, which says if I have some function rho here of x and y, so two variables x and y, then if I first minimize with respect to x and then maximize y, that's always going to be less than or equal to first maximizing with y and then minimizing x. So note that we're always minimizing with respect to x and we're always maximizing with respect to y. It's just the order of min and max is swapped. Okay, and in that case, we know that when we first maximize and then minimize, it's always going to be larger than first minimizing and then maximizing. And the whole point of this ordering is just like what elements of our function, what parts of this input are we actually dropping when we do a minimization or a maximization technique or function. Okay, and so you can build out this fact as follows. So let's just start with our function rho. Well, firstly, we know that if I take the minimum of the function with respect to x, that's always going to be less than or equal to all other functions, or all the output of the function at all other points. So because I've taken the minimum of x, I know that I'm going to be at least less than or equal to any of the other points in that function. That's somewhat obvious. Similarly, I know that when I maximize with respect to y, that's going to be larger than any of the other elements in that function, which is already larger than the minimum. So I know now that if I maximize with respect to y of this function, it's going to be larger than if I minimize with respect to x of the function. Okay, similarly, I'm then going to now maximize on the left-hand side with respect to y, but I may have already dropped the variable that maximizes just the function directly, may have been dropped when I minimized x. Okay, that's the worst case scenario. Best case scenario, whatever element maximizes the function is still in the set after I minimized x. And so now when I maximize for y, I'm still going to get to the same output. Okay, but it cannot be bigger than maximizing directly, because by minimizing x first, I may have restricted my function to a region where it's actually going to be lower. Okay, and so this second maximization on the left can not go any higher than just maximizing directly. And then lastly, the same idea holds when I minimize on the right, because now I have first maximized and then minimized. I haven't restricted the set to be the minimum values first and then seen how large I can get in this restricted set. Instead, I've restricted myself to large values and then seen how low I can go in that large set. Okay, so on one end of the spectrum, I have, let's maybe draw a set of axes. So I have an axis here. I'm first restricting myself to the large region of output and then finding the minimum point in that region. And then in the second case with this blue over here, I am first restricting myself to a minimal region and then finding the largest point there. It's kind of dumb of me to use the same colors. Let's draw this better. Okay, so green. So I'm finding a large region on the right-hand side here and then finding the minimum point in that green region. Okay, this minimum over there. And then on the right-hand side, I am first going to find a minimal region in the output. Okay, and then after that, I'm going to find the maximum point in that region. And you can see here that the yellow line is now lying below, okay, it's lying below the red line. Okay, so it's just about these orderings that I've restricted my output magnitudes. Either I'm finding the smallest of a large set or the largest of a small set. And so on the right-hand side, it's the largest of a small set. On the left-hand side, it's the largest of a small set. On the right-hand side, it's the smallest of a large set. All right, and that's called the min-max inequality. And that's going to be useful immediately in a second. Okay. The second concept we need is just called weak duality. And so namely, the primal values are always greater than or equal to the dual values. And so this is kind of why we kind of might want to work with the dual problem. But let's just say we're going to start by looking at this j function. All right, you'll remember that this was j of x over here, was that term there, with our infinite sum of infinite step functions on the right-hand side there. So we're going to minimize f of x and then make sure we don't violate any constraints. That was equal to j. And actually what this is the same as is taking our Lagrangian and maximizing lambdas first. Okay, and if you scroll up to the top here, you can see that. So this is our Lagrangian. If I say, well, how large can I set my lambdas? Well, in this case, we just set them to be infinite. And once again, anytime these g's are now greater than 0, we get positive infinity on the right-hand side. So actually this j function that we've been kind of avoiding saying was a bit rigid actually corresponds to a case where we actually just maximized lambda first, okay, for our Lagrangian. Okay, and so this is now going to correspond to having the full Lagrangian on our right-hand side here. And that's interesting because now by writing j in this form, we've actually put ourselves in a position where we can use the min-max inequality to maybe make this problem a little bit easier. So we know that this problem here, this j, is going to be our largest possible penalty. It's actually going to always be this really large, the function is always going to output this really high value, or at the very least, if we aren't violating any constraints, we're just going to revert back to f. So if we are trying to solve the original problem using j, then we were looking for this term here on the right, where we take our Lagrangian, we maximize the lambdas, and then once we've constrained ourselves to the region of this function space, or the input space of this function, where L is as kind of strict as possible on the constraints, where we know we don't violate any constraints, then we just find the minimum point within that region. That corresponds to our primal problem, and we know that that was a little bit too strict and is really, really difficult to optimize. On the flip side, as I said, we can use the min-max inequality now, so that instead of first maximizing lambda, then minimizing x, we instead minimize x, maximize lambda. And we know that, yes, when we use the min-max inequality, the term that gets first minimized, then maximized, is going to be less than the version of this equation that first maximizes and then minimizes, right? That ordering method. So we know that our dual is always going to be slightly less than our primal problem. And so that is a little bit of a concession that we need to make, because we know that we're not going to maybe fully optimize completely, but at the same time, at least this is going to be a little bit easier to solve. Okay? And so the right-hand side is what we are solving the dual problem, which is a lower bound of our primal problem. It is slightly optimistic because it's a lower bound. But equation 20 represents, and this kind of lower bound, represents what is called weak duality. And if we're in a case where it's equal, then it's strong duality. And the difference between the left-hand side and the right-hand side here is called your duality gap. So this duality gap says, well, how optimistic is our representation of the problem when we're considering the dual rather than the primal version? How much am I actually missing in terms of optimizing our function due to the fact that we're actually going to try and solve the slightly easier version of this problem, where I first optimize the variables I care about, then see how strong I can get on my constraints, rather than being super strong on my constraints and then optimizing within that valid region. Okay. So the dual objective function is an unconstrained optimization problem for a given value of lambda. And again, unconstrained optimization problem here. In this case, we only have one variable, and it is, the lambdas must be greater than or equal to 0. That is actually a constraint on them. But it's not the same way we have a constraint on x, where the output of a particular function of x must now be less than or equal to 0. we're not optimizing for any other functions of lambda other than just this dual over here. And so that's why it's saying that it's unconstrained there, which again makes this slightly easier to work with. What this ultimately means is that we actually know that the function is convex with respect to the lambdas. Okay, and so if solving the minimum of a Lagrangian for a fixed lambda is easier, then the overall problem is easy to solve. Otherwise, we can observe that the Lagrangian is affine with respect to our lambdas, and therefore, if we minimize x of our Lagrangian, we will get the pointwise minimum of affine functions of lambda, and hence the dual problem is concave. Sorry, not convex, it's convex, as I said earlier, it's concave, even though f and the gi's may be non-convex. Okay, so that's a bit of a mouthful, but the whole point of this is to say if we go up and look at our Lagrangian up top here, let's see where we've written it. So this is our Lagrangian over there. You can see that we've substituted that in there. What it's essentially saying is that it's an affine function of our lambdas. And we know that what an affine function is, and we can even, maybe we go back to the proper version of this. Here. It's an affine function of our lambdas, this Lagrangian, because we have some shift term, all right, that's a scalar value, f of x. So we have some shift and then some linear vector that is multiplying our lambdas, okay? So we have some kind of shift and some kind of matrix operation, some linear mapping of our lambdas. That is an affine function, okay? And the whole point that this is now affine is because these two terms are fixed once we've minimized over x. Okay, once we minimize x, those are now somewhat static, or at least we have expressions for them which make those functions behave as if they're constant. They're no longer variables in that expression, which means that when we're working with this dual and lambda is our only variable to optimize, this is now a really simple concave function. Concave because it looks like that. Okay? And so what that means is that now we are in a regime where we're actually working with some really kind of quite a simple function that is much easier to optimize. And because it's concave, similar to when we're talking about convexity, we're now going to have kind of unique solutions to this problem. And so this is essentially what the slide is saying. It's trying to make the point that now once we've minimized for x, we found expressions for x that minimize the Lagrangian, we're now in this really nice regime where we can solve this for this Lagrangian term. We can solve the dual problem, and it is a concave, even though the functions that we were originally dealing with, the f's and the gi's, were themselves maybe non-convex, really complicated functions. Okay, so again, we've now turned something that may have been arbitrarily complicated into a single concave function, and that's now going to make our problem much easier. And in particular, this works well when it's easy to first solve for x. If we're in a case where solving for x is hard, then obviously we don't want to represent that as our first step to solving the problem. But in more cases than not, solving for x first is quite a lot easier than trying to set now these like arbitrarily large lambdas. Okay, so now we're going to say assuming f and the gi's are differentiable and convex, we can find the Lagrangian dual problem by differentiating the Lagrangian with respect to x and setting the differential to 0 and solving for the optimal values. And I'm going to walk you through examples of this now. But essentially, this is the strategy, right? We're going to, in particular, you want to have differentiable. Obviously, as we just said, even if these are non-convex, we can still use this. But we're going to look at problems in the rest of this course or this rest of this lecture where these functions are still convex. Excuse me. So that's where we're at. And the one kind of caveat just to mention before we move on to that is our original formulation only deals with inequality constraints. We have our gi's less than or equal to 0, but you can extend the discussion to include equality. That's the them they're talking about here. You can include equality constraints, as you can see in the title. And so in this case, you have our hj is equal to 0. And you can replicate the previous arguments in this case with the inclusion of equality constraints. And to do this, you just need to recognize that an equality constraint is just the same as saying that a function must be greater than or less than, then greater than or equal to 0 and less than or equal to 0 at the same time. In other words, the only function that satisfies both is equality. Okay? And then obviously we always want our constraints to be less than or equal to 0, so it's the same thing as saying negative hj of x less than or equal to 0 and hj of x is less than or equal to 0. Okay, these now both fit the form of a g variable, and we're back to the original formulation we had. Okay, so not super difficult, it's just a way of representing a quality with two different inequalities. And then lastly, for many practical problems, this is also a little bit strict. So instead of having 0 over here, you will have epsilon. And so in that case, you'll have minus hj of x minus epsilon less than or equal to 0 and hj of x minus epsilon less than or equal to 0. Okay, and again, that's a slightly weaker form of these constraints, but sometimes it gives a little bit of slack on how dogmatic or how kind of specific we need to be about our constraints. But anyway, we won't necessarily look at that too much now. Okay, so we're nearly there. We've now caught back up to the middle of these slides where I originally started. So now I'm going to kind of step through that and jump to kind of the last few slides of this lecture. So I'm now picking up on slide 18. I was on slide 11. In summary, from what we've just discussed, a constrained optimization problem is called a convex optimization problem if we have the following equations. So you're trying to minimize a function f of x subject to a constraint gi of x is less than or equal to 0 and subject to some equality constraints or hj's. Okay, and so we're going to now look at two kind of versions of this problem and how to solve them. The first is called linear programming. Okay, and so the following is a linear program of d linear variables and m linear constraints, and so it fits the following format. Okay, so our f of x in this case is that we want to minimize over the x's, and we have some c vector dot product with x subject to a matrix multiplication of x must be less than some b threshold. Okay, and you can see the shape of our matrix there. Ultimately, we have m constraints defined by the b's, and we map our we map our d dimensional problem onto those m constraints using a. Okay, and so to begin with, we're going to just form our Lagrangian. So we know that the way we form our Lagrangian is to write f of x first. We just literally drop f of x in. Okay, and then we write our set of constraints as follows. So firstly, we're going to take this bit over here, and we know that all of our gi's of x must be less than or equal to 0. So we're going to say instead of ax is less than or equal to b, we're going to say ax minus b less than or equal to 0. And so now that fits the form that we really want it to be in. So that's good. And we're going to drop that into our equation and multiply by our lambda. Okay, so there's our Lagrangian, the lambda transposes, being multiplied by our constraints on the right-hand side of it. Okay, so that's step one, right? Write your Lagrangian. Step two, you can, if you want, kind of simplify, and that's what they do in the slides here. So they just FOIL this out using the linearity of that dot product, and then group the terms around x. Reason being is we're now going to actually differentiate with respect to x. Okay, so you can see here that the lambda is the vector of non-negative Lagrangian multipliers, and from here you can find the dual problem by just minimizing with respect to x. Okay, that is step 2, and that's what follows now, is that to find the minimum of a function, we know that to do that you just take the derivative, set it equal to 0, and solve. Okay, and that is exactly what we're going to do. So the minimum is found by using the gradient. Remember, we're dealing with a convex function in this case. And again, not all of them have to be convex functions, but because we are, you can just differentiate with respect to x, and you get something, excuse me, you get something quite well behaved out of this. So in this case, we're going to differentiate this Lagrangian with respect to x, and that just falls away. This term on the right-hand side has no terms of x, so that just falls away. And what we're left with is c plus a transpose lambda, c plus a transpose lambda is equal to 0. Okay, and so that gives us a constraint. There's no variable of x anywhere, so there's nothing to optimize here. But you do come and substitute this back into our original function, which is then step 3. Okay, step 3, sub 39 into 36. So, or let's just do 37. Okay, number 2 was differentiate. And 1 was form Lagrangian. Okay, those are the 3 steps. So what we've done now is we've said, well, okay, I know that x is optimized when these terms are the c plus a transpose lambda is equal to 0. And so I'm just going to come and drop that in there. All right. This then means that that evaluates to 0. That gets dropped off. And so you end up saying, well, this min of x here, min over x, is equal to negative lambda transpose b, which is the definition of our joule. And that is it. Those are the 3 steps to deriving the joule optimization problem from a linear programming problem. Okay, and so if you look at your tutorials, which I hope by now you have, you'll see that a lot of these questions are actually just asking us to derive this, because from here you're now at a concave function, and so this is, you know, standard to optimize. You've now gotten rid of any sort of constraints. We know that the lambdas just have to be greater than or equal to 0, but that's about it. You can actually just try and directly solve that now. And, you know, there's obviously algorithms like gradient descent and that sort of thing, which are all applicable once again. So those are the 3 steps. And again, it's very formulaic. Linear programming, you first form your Lagrangian, you kind of simplify if you feel you need to. You then second differentiate with respect to x, so you can optimize for x, which gives you the ability to then substitute your optimal values for x back into the Lagrangian, so you get your joule. And from that, you've now derived your joule, and you've removed x from the equation, and you're just left with optimizing and getting your lambda constraints as large as possible. Okay, and so there is also a general form to these. So if ever you're in a position where you know you've got a linear programming problem, you can generally then just jump directly to the joule optimization problem, which has the following properties. So you have the joule now, or the function now, which you're going to optimize with respect to lambda. In this case, it's not completely unconstrained. You know that those terms must be equal to 0. And then lastly, lambda must be greater than 0. This is also a linear programming problem with m variables. And so, you know, kind of what I was saying earlier about them being, the lambdas being unconstrained is not always completely true. But you now have the choice between optimizing in the primal or the dual space, and depending on whether or not m or d is larger, is which one you'll choose. And in more cases than not, these the second equation is much easier to satisfy, at least, and there are a lot less lambdas than x variables. And so you can now kind of reduce at least the dimensionality of your problem, and the kind of avoid this curse of dimensionality issue we have with large x's. So none of the slides kind of jump around saying things like it doesn't need to be convex, this f doesn't need to be convex, or it does, and stuff like that earlier. But just remember that there are kind of different versions of these problems, and a linear programming is just one of them. All right. So I think it's good to understand the general idea of convex optimization, this Lagrangian optimization, and then linear programming is just kind of one instantiation of these techniques. We'll see another one now, which is quadratic programming, which fits those assumptions a little bit better, or fits those kind of statements a little bit better from what came earlier in the slides. But if you're looking for a little bit of visual intuition for what's going on, we have our different functions, our different constraints, which are drawn in this image at the bottom here. So we have these different lines all intersecting, and we're trying to avoid violating any of these constraints. And so you're restricted to optimizing x within the shaded region over here. And that's largely what we're doing, right? We're trying to find ways of solving that problem, either by working in the x space or defining different variables, your lambdas, and working in that space. Okay, similarly, we can work in a quadratic programming. So it's the same kind of idea as we just saw with linear programming. So the following is a quadratic program of d variables and m linear constraints. But now your function that you're trying to optimize has a quadratic term with respect to x. So it's a term where you have two x's instead of just one. Same story though, A is a matrix that maps your x's onto some kind of constraints. Your constraint term is the same as before with m constraints, and C is some kind of dot product of x as we had before. So everything is the same as we had with linear programming. Just now we have this term out front, this quadratic term out front, with this Q being a square matrix, and we're going to assume it's positive definite so that Q inverse is well defined. Okay? That's ultimately where we're going with this, is we're going to need that to solve this problem. You can see in the footnote, we consider the positive definite case, but it's not always necessary to be that strict for convexity, but positive definite cases mean that Q is invertible. So similar to a lot of points in these slides, sometimes you make a bit of a strong assumption, but it makes solving your problem quite a lot easier. Okay, so in this case, that then means that the objective function is number 45, equation 45, is once again convex. And we know earlier it said that there are versions of these problems where it's not necessary for it to be convex. But again, we're going to only consider these convex problems for now. Cool, so let's see how we solve this again. And once again, there are 3 steps. The first one is to just write your Lagrangian. Okay, there is my constraints. Once again, you want your constraint in the form ax minus b less than or equal to 0, which is exactly what we've done with this over here. Your constraints are multiplied by your Lagrangian multipliers, and then anything after that, we just take this term f over here and drop it in directly over there. Okay, so that's step 1, form the Lagrangian and simplify if you want. Okay, secondly, we're now going to try and minimize the function, this Lagrangian, with respect to x first, so that we can substitute the answer back in to get our dual. Okay, so come through here, and I'm going to actually write the 2 next to the derivative. So you're going to differentiate the Lagrangian, and so we end up dropping this term off the front here, dropping that term there, and then this becomes 0 because that had none of the terms, that had none of the no x variable. One thing that just to mention that we're doing here is we're also taking this term and we're using the property that AB transposed is equal to B transposed A transposed. And that's what we're doing over here. And we're saying that X transposed Q is equal to Q transposed X. But Q was, again, an invertible matrix. We know that it can be written as a symmetric matrix, and so we have Q of X. All right, so Q of X is out there, and we've instead just taken our transposed out and groups it out the front there. Okay, so again, I'll write that out once more. We're going to transpose this term, so we end up with Q transposed X, all transposed. Okay, using this property at the top left over there. But lastly, we can then also note that Q, by assumption, is symmetric. And so we're left with this term out front. And so now we can then just group. Ultimately, we end up with, let's clean up a little bit. We end up with this term here. That is QX transposed plus C plus A transposed lambda, all transposed. And now we have these 2 transposers out here at the top. And so we're just going to group these terms to be equal to qx plus c plus a transpose lambda, and then we just put the big transpose around all of them. And that's how we end up with this term over there. All right, so a little bit of manipulation. You don't have to go too into detail with it if you just jump to the equation 50 when you write this out. That'll also be fine in a test, for example, if it came up. Okay, so you now minimize your Lagrangian by taking the derivative and setting it equal to 0, and that's equation 50. But now we have this x term, so we do need to actually solve this equation with respect to x, but that's quite easy because all we're going to do is take this term over the equals, okay? And so you get negative of that term, and then lastly, we just need to invert, so we end up with qx is equal to negative c plus a transpose lambda, and then on both sides, we're just going to write q inverse and then q inverse. That drops away, and so you're left with just x over here is equal to the negative q inverse times by c plus a transpose lambda over there. Okay, and so that's that part of the derivation there. So you've just, again, followed the same formula, just a little bit of manipulation. You write your Lagrangian, which is step 1. Okay, step 2, you differentiate that, just dropping your x terms on either side. And then lastly, you solve for an x value there. You're now going to take equation 51 and substitute it back into equation 48, and we're going to do that now. So first things first, we had this x variable over there, and we have this x variable there. We're going to leave this term here for a moment just because it's a bit unwieldy to work with. So we're going to take this equation here and substitute it into that x there, and this is what we get by doing that below. Okay, once again, using the fact, or I guess we can leave that for now, and then just go back and consider what's happening on our left with the quadratic term. So again, we're going to drop in our representation of x into those two terms there, and this is then what we get. We still have our q over there is this q over here, and then this is one of our x's, this is the other one of our x's. Just note that this x on the left hand side is transposed, and so we have this transpose there. Okay, it's this brackets here, transposed. That's it. All we've done is substitute it in for x. Now we're going to use that same transpose rule we had before, where it's a, b, transpose is equal to b transposed a transposed. We're going to use that over here, and so you end up rotating or kind of flipping the ordering of our variables. So the one variable here, our b, is essentially this term in the brackets, and our a is the q inverse. So we're just going to flip that ordering, and so you end up with c plus a transpose lambda all transposed times by q inverse transposed over there, and so we've now applied this transpose up here and simplified accordingly. Similarly, from the right hand side of our substitution, we had our second x variable and the original q, but you can see that these two q variables are next to each other, and so they cancel out. So on the right hand side, you actually then end up just sticking with that c plus a transpose lambda. And so once we simplify, we end up with q inverse transpose in the middle. Again, we can just drop that transpose because we know that those are symmetric matrices. And so you end up with something pretty clean, just another quadratic form in terms of lambda. Okay, and what you'll notice is actually this is half of what this is. Okay, and so this is a minus of that term, and so you end up with a half minus 1 of those same terms, and so when we put it all together, you get minus a half. Okay, and this term on the right hand side here stays the same. All right, and that's it. That's the entire derivation. You just substitute in back into the function. So equation, sorry, let's clean this up. Okay, so equation step 3, equation 51 subs into equation 48. Okay, and that's now it. Once we've done a little bit of simplification with our transposers and cancelling out the inverses, the only thing left to do is just to recognize that it's a half minus a 1 gives us a negative half. And so that's our dual problem. Derived. That's it. That's how you derive your dual problem. And so when you write it out, in this case, you now get, again, it's still, there is this constraint of lambda greater than or equal to 0, but it's a much easier problem to work with, especially if m is much lower dimensional than d. Okay, and so this is used a lot in things, for example, like support vector machines and kind of other kind of areas of like kernel regression and things like that. That is it for the slides. We're not going to cover convex conjugacy and those sorts of things. They're kind of, I feel, pretty thrown in at the end of these slides anyway. I'll leave them in for your own interest if you want to look at it. But this is the end of the course as far as I'm concerned. And you do have some tutorials on these questions. And I suggest you kind of get some practice at deriving these joules. But again, the formula is always the same. It's the same 3-step process. And then on top of that, you just kind of, I think it's important to appreciate the reason these things work and why in particular that min-max inequality is so important, and the relationship between the primal and the dual functions, I think are kind of like the key points of insight in this section. All right, that is the end of the course. I kind of hope this last video, I went through it, I think, fairly quickly, but hopefully that all makes sense. And we can chat before your exam if you need any help with these concepts. All right. Thanks, everyone.